So we've started to drift off into the complicated world where you thought that there were only three kinds of particles a few weeks ago. Now we've started to talk about antimatter, and we've started to mention a few different particles. Well, here's a whole new kind of aspect of this, things called quarks. Okay, we need to know what a quark is, what types of quarks there are, and how do quarks combine to form some forms of matter. So things like protons and neutrons, which so far you've thought were fundamental particles, that means ones that aren't made of anything simpler. Well, in fact, they are made of something simpler. They're made of these things called quarks. How do we know that? Well, think about the evidence for the nuclear model of an atom. You remember Rutherford scattering. What did Rutherford do, or what did he get Geiger and Marsden to do? He got them to fire alpha particles at atoms, and what he noticed is a few of them were backscattered. What that told him was that there must be not mass all the way through the atom, but a small dense region of mass in the centre, which was strong enough to repel, so dense enough to repel the alpha particles, and also positively charged. Okay, that's how we knew that atoms weren't plum puddings, how we got to the nuclear model. Okay, he made this model of the atom and magically explained the entire periodic table with just three particles. That was great, but unfortunately life isn't actually quite that simple. Okay, this much underrated man that you should know, Murray Gell-Mann, he was the person that proposed that as they were finding more and more subatomic particles, he said this is just crazy, there can't really be this many particles, in the same way that people started to realise that there probably weren't 100 different sorts of particles that were all fundamental to make the periodic table. They must be made of just three simpler particles. Okay, Murray Gell-Mann had the same idea. He said, we've got dozens of subatomic particles, maybe this is just a simpler set of particles joined together in different ways. Okay, he called these particles quarks, and he said they have 6 flavours. So we have to, in the same way that we invent ideas like charge, we have to call it something, so we call them flavours. And those are up, down, strange, top, bottom and charm. The good news is that you can imagine joining 6 things together in different ways is quite complicated. We ignore top, bottom and charm. We only worry about the up quark, the down quark and the strange quark. How did he prove this? Well, they did electron scattering experiments. So in a similar way, what they did is they fired very high energy electrons at the nucleus, and they found that some of the electrons bounce back. What does that tell us? Well, it tells us that there must be a very small dense region in the centre of the protons and neutrons, and also, most surprisingly, that that region must be negatively charged because it's repelled electrons. So this told us that particles are made of quarks, and some of those quarks are negative, and there are 2 classes that you need to know of what are called hadrons. Hadrons are particles which are made of quarks. And the first class is called baryons. Baryons are made of 3 quarks. Notice these are not antiquarks because there's no bars on the top. And what baryons do you know? Well, at the moment we know the proton and the neutron. And these are only made of up and down quarks. And here's our up quark. It's got a charge of plus 2/3. The down quark is a negative one. That's got a charge of minus 1/3. This information's on the data sheet for you, so you haven't got to learn it, but it's handy if you become familiar with it. So to work out the quarks in a proton, well, we know the proton's got an overall charge of plus 1, but it can only be made of these quarks. Okay, it can't be 3 up quarks because that would have a charge of plus 2. It can't be 3 down quarks, that would have a charge of minus 1. What we end up with is 2 up quarks has a charge of 1 1/3, and 1 down quark minus 1/3 to give us an overall charge of plus 1. And the neutron is 2 down quarks, so a charge of minus 2/3, and 1 up quark plus 2/3 to give us its neutral charge. Okay, so here's our first 2 hadrons. These are the only 2 that you need to know specifically. Okay, but there are lots more. You can see that by the time you've joined different quarks together, there's a lot of different possible baryons that you could make. Okay, here's our new picture. So a proton, which we thought before was just a big solid circle with a plus on the middle to tell us, is in fact made of 3 quarks, 2 up quarks and a down quark. Here's the neutron, an up quark and 2 down quarks. Okay, this picture's not very good for lots of reasons. Okay, mostly because the quarks are only about 10 to the minus 19 meters across. Okay, so interestingly, just when you thought that atoms were almost entirely empty except for that big solid bit in the middle you call the nucleus, it turns out that the nucleus is mostly empty as well. So these quarks are tiny little dots inside this thing which we call the proton, but it's in fact mostly empty space. Okay, I'm going to ignore all the way through this the colour charge, but these things have a different property called colour, and you'll notice that they end up being white because we've got a red, a green and a blue. Those three primary colours make up white, but after this I'm going to just ignore the colour charge. You don't need to know anything about it. Okay, don't worry about it. Okay, here's our second class of hadron. These are called mesons, and mesons are made of a quark and an antiquark. Okay, that's Q and Q bar. Okay, the first one that was discovered was a pi meson, it was called originally, but now we just call it a pion, symbol pi. And pions only contain up and down quarks. Okay, so you could have two ups, you could have two downs, or you could have an up and a down, but remember, one of them is a quark and the other one has to be an antiquark. That gives us 4 possible pions. Okay, and we can work out the charges of those 4 pions. So here they are. We can have an up and an anti-down. So here's our thing, a quark and an antiquark, and only ups and downs. This has got a charge of plus 2/3. This has got a charge of plus 1/3 because it's an anti-down. So we've got plus 2/3 plus another third. That makes plus 1. What you'll notice with it is when you end up with an overall particle, you'll always end up with a whole number. So you can't combine these in any way to make a charge of like plus 2/3 or 1 1/3 or something. It always ends up as a whole number. So this is an up and an anti-down, and it's a pi plus. If we have an up and an anti-up, well, that's got to be a pi 0 because that's plus 2/3 and that's minus 2/3. We can have a down and anti-down, that's also a pi 0 because you've still got an overall charge of 0. And we can have a down and anti-up, that's minus 1/3 minus 2/3 gives you a charge of minus 1. So there's our first class of meson, things made of quarks and antiquarks, and it gives us these different particles. Okay, after they looked at mesons for a bit, they realised that some mesons seem to behave a bit strangely. They actually lasted much longer, so all these particles are unstable, they all decay, usually in millionths of a second. But some of them seem to have half-lives which are much longer. They said, oh, this is a bit strange, maybe they're not the same, and so they invented this idea called a strange quark. It's also got a charge of minus 1/3, so it's like the down quark in terms of its charge. Okay, but it's a different sort of quark. And they call these sort of mesons kaons. So kaons are particles that have always got a strange quark in them or an anti-strange quark, and they've either got an up or a down. So again, there are 4 possible kaons. Okay, we can have an up and an anti-strange. This is a K plus. We can have a down and an anti-strange. That's minus 1/3 plus 1/3, a K 0. Okay, here's its antiparticle, and a K minus, which is a strange and an anti-up. Okay, so 4 possible kaons as our second kind of meson. You need to know those 2 sorts of mesons in detail and be able to work out the quarks. Okay, don't try to learn them all. Just know, for example, if it's a K plus, you know it's a kaon, so it must have a strange quark. You know it's a meson, so it must have a quark and an antiquark. Okay, by the time you've done that, you should be able to work out that it must be up anti-strange. Okay, one thing to really confusing is that the K plus was the first kaon that was found. We now know that the quarks in it are an up and an anti-strange. So we gave it a number called strangeness. This is another one of these quantities that we'll talk about soon about conservation. So like charge, this is a property which is always conserved. And so it was given a strangeness of 1, even though it had an anti-strange quark in it. What this means is the anti-strange quark has got a strangeness of 1, but a strange quark has got a strangeness of minus 1. You might be shaking your head and thinking, what's he talking about? But don't worry, because when we look at conservation laws, you'll see these are very important ideas for us to know what might happen, what equations are possible and which ones are not possible when these particles decay. Okay, so although there's only 2 baryons that you need to know, right, they might give you questions on the exam which are about baryons you've never heard of. So here's a sigma plus particle, for example. Okay, they'll tell you it's a baryon and it's got a strangeness of minus 1. So if you break that down, you know it's a baryon. That means it's got 3 quarks. You know it's got a strangeness of minus 1. That means one of those quarks is strange. You know its charge is plus 1. The only way you're going to get to plus 1 with a strange quark is to have 2 up quarks. So you can work out an up and an up and a strange. What's that got? It's got 3 quarks. That's right for a baryon. It's got a strangeness of -1. That's right, because it's got a 1 strange quark, and the strangeness of a strange quark is -1. And plus 2/3 plus 2/3 minus 1/3 gives you a charge of +1. So even though you've never heard of a sigma plus, if you can learn all the rules, then you can work out what the quarks are. Here's a delta minus. It's not strange. It's a baryon. It's got a charge of -1. Okay, this has got a down, a down, and a down. It can't have an up because we wouldn't get to the right charge. It can't have a strange quark because it's not strange. Okay, it can't have any antiparticles because it's a baryon, and baryons are made of 3 quarks. Okay, there you go. Here's a delta plus plus. That's actually 3 up quarks. That's the only way you're ever going to get to a charge of +2 with just 3 quarks. Okay, so if you learn the rules, you can actually answer lots of questions which you think at first time, you think I've never heard of these particles, but you can work out what quarks they must be made from.